Hello and welcome back to Calculus 2, section 10.5 on comparison tests, also known as the last resort. What we have here are two tests. One is called direct comparison and the other one is called limit comparison. Now, in order to be successful with these tests, you need to be well versed with p-series, because most of the time you will be comparing to p-series. Sometimes you will compare to geometric. I mean, it depends on what the series looks like. But the title tells you what's going to happen. You are going to compare the series you have to different series that you know how to do, and then draw conclusions from there. Now, there will be conditions and a little calculation you have to do every time. But as I said, if you can use some other test that it's more straightforward, then use that test and leave this as a last resort when everything else fails. So, two comparison tests. The first one is direct comparison test. So let's go with the direct comparison test first. In the direct comparison test, you will be comparing the sequences within series, right? Sequences, and then you will draw conclusions observing the situation you have. So let's first write the theorem. So let summation an and summation bn be series with positive terms. So that's a condition, right? The series that you want to solve has to have positive terms. And here are the two comparisons you can make. If an is smaller or equal than bn, and summation bn converges, then summation an converges. And number two, if bn is smaller than an and summation bn diverges, then summation an diverges. Let's see this in pictures. Number one and number two. So what you have here is the n on the axis and an on the y-axis. Sorry, not an, sorry. Just leave it empty because we'll have two sequences. So here is a sequence, a series that is behaving a little bit irradical, right? And that's your an. And you are looking for the sum of an. But it's all over the place and it doesn't fit any of your tests. If you want to do the comparison, question is, can you find a convergent series bn that is bigger than an? So every point of bn is higher in value than every point of an, the corresponding point of an. Which means that bn cannot be crossed by an. An is always in between the x-axis and bn. So it's squeezed in between. So what's happening now is that the an, which we don't know whether it converges or diverges, is squeezed between the convergent series on top and the 0, which is the x-axis on the bottom. And it has to converge, right? Because it's kind of funneled into convergence. So that's one situation. The other situation is for divergence. Now you're looking for some series that it's smaller. So your Bn now is less than An, and it pushes An into divergence. So that's what those mean, those up there. So when you have a series you can't solve, you say, all right, so let me try and find a smaller series that would converge, or a larger series that would converge. So let's take a look at an example of this. Say you have summation of 3 over 2 to the n plus 1, going from 0 to infinity. Now you're looking at this and you say, that plus 1, right? Without plus 1, this would be just a basic geometric series. You have 1/2, it converges, you're done, right? But that plus 1 ruins everything because of that plus 1, it's no longer geometric series. Now, it's not geometric series, nothing else works, therefore we are stuck with our comparison tests. So you extract An, which is 3 over 2n plus 1. And now you say, well, without this plus 1, this would be a convergent sequence. So convergent series. So I am thinking this should converge. So let's try and use Bn as 3 over 2 to the n, whose series Bn would converge. Which means that this should converge, but before we can claim that, we need to show condition which is An less equal than Bn. So if we are able to establish this, then we can immediately claim convergence on An, because you would have all of the criteria from the theorem fulfilled. So I need to show that 3 over 2n plus 1 is smaller or equal than 3 over 2 to the n. Well, we cross multiply. 3 times 2 to the n should be less equal than, you can put a question mark, 3 times 2 to the n plus 3 times 1 is 3. Now if you consider that these two are the same and this side has a plus 3, well, clearly the right side is bigger. Therefore, this is true. And now we can provide an answer. Since three over 2 to the n is larger than 3 over 2 to the n plus 1, and summation 3 over 2 to the n 0 to infinity converges by geometric series, summation 3 over 2 to the n plus 0 to infinity, converges by direct comparison. We look at the problem, we decide whether the problem should converge or diverge by looking at the form of it, and then we compare it to something that makes sense. Let's see another example. Say you have summation of 4 divided by n plus 3 from 1 to infinity. So you look at this and you say, when I take away all the fluff, which is a 4 and a plus 3, this looks like 1 over n, right? And what do we know about harmonic series from last class? We know that harmonic series diverge. So we expect for this to diverge, so we can try and compare this to 1 over n or 4 over n. We can use 4 over n, it's fine. So my an is 4 over n plus 3, and I pick bn to be, let's say, 4 over n. We know that summation of 4 over n is going to diverge because it's harmonic series. We learned yesterday that harmonic series a over n diverges. That's what we learned last class. So we are expecting this to diverge, which means I need to show that bn is bigger than an. No. bn needs to be smaller than an, needs to be underneath. Need to show this. So bn is 4 over n, and that needs to be smaller or equal than 4 over n. Put n minus 3. Need to have n minus 3, because if you put a plus, then we have to use the limit test. We didn't learn everything yet, so there's supposed to be a minus 3 there for this problem. So now what do I do? Well, again, the same thing, cross multiply. I get 4n minus 12 needs to be smaller or equal than 4n. Well, 4n is the same as 4n. Negative 12 is less than 0, so this is true. And now I have everything. I have that the bn is smaller than an. I have that the bn in a summation diverges, therefore an must diverge as well. So answer, since 4 over n is less equal than 4 over n minus 3, and summation 4 over n diverges as harmonic series, guys, you don't have to say harmonic series, you can say diverges by p series, diverges by integral test, whatever. So since this is the case, and diverges as harmonic series, then summation 4 over n minus 3 diverges by direct comparison test. Now, direct comparison test is very rarely used because the more powerful friend, called the limit comparison test, steals the spotlight 99% of the time. Obviously, if the problem says use direct comparison test, then you have to use direct comparison test. The reason why people don't use direct comparison test is because you have to do this proof every time to show that either A is larger than B or B is larger than A. And that proof is the one that a lot of people don't want to do. So they go to the limit comparison test, and the limit comparison test asks you to take the limit of the quotient of the two A and B sequences. So let's take a look at the one that it's used most of the time. Limit comparison test. So for the theorem, we have the same deal. Let summation an and summation bn be series with positive terms, and let the limit as n goes to infinity of an divided by bn be equal to L, which is finite number. I'll just put finite. Number one, if 0 less than L less than infinity, so if you have a finite number bigger than 0, then both either converge or diverge. They have the same fate. Then both summation an and summation bn converge or diverge together. Number two, if L equals 0 and summation bn converges, then summation an converges. And last one, if L equals infinity and summation bn diverges, then summation an diverges as well. So these comparison tests are listed on your sheet halfway through under integral test, and these are the conditions for the limit test. Now, limit test, it looks like a lot of stuff to remember there, but technically all you're doing is you are taking the limit of the quotient over there. If you get a finite number, it's going to converge, right? And if you are getting infinity, it's going to diverge. Now, if bn diverges, then through 1 diverges as well, right here. So now it's a good time to take a look at the same problem we had, but this time instead of -3, we put +3, which is where the direct comparison would fail, and you would have to use this method to solve the problem. So summation 1 to infinity of 4 over n plus 3. So this was a problem with the plus. So problem with the minus, we solve using direct comparison. Now you can do the limit as well. We extract an as 4 over n plus 3, and since this reminds us of a P series with a harmonic series, right? We say Bn is 4 over n. Now we know that the summation of 4 over n diverges because of the P series, or integral test, or harmonic, whatever of the three you come up with. So now limit n goes to infinity, an, which is 4 over n plus 3, divided by bn, which is 4 over n. And you just need to solve this limit. So these 4's will cancel. And we have limit n goes to infinity of n over n plus 3, which is equal to 1. Sometimes you'll have to use L'Hopital rule to solve this. So now that we have that the limit is, well, that's like saying L is equal to 1. Guys, it's the first condition here. And we know that this one diverges. Right? So now we write the answer. Since L equals to 1 and summation Bn diverges, the series summation 1 to infinity of 4 over n plus 3 diverges by limit comparison test. Limits can be tough to solve, right? So sometimes maybe your direct comparison is a good choice, better choice. But you know what? Limit comparison test works in 99% of the cases. So it's better if you know limit than direct. I mean, no, both, obviously, but limit one is the one that it's used most of the time. So it's time to take a look at some problems from homework and see what kind of monstrosities they have in here. You have to be good with p-series because most of the sequences you're going to compare with will be some form of the p-series looking problem. So let's take a look at a whole bunch of these problems. Some of them are very tough and some are very easy. So this would be considered easy. Summation 1 to infinity of n squared plus n minus 1 divided by n to the fourth plus 4n squared minus 3. So this is considered easy. And you can use either of the two comparison tests. Now, when you look at this, what is the order of the entire problem? If you were to simplify using bad algebra, what would you get? Using bad algebra means ignore all of the lesser terms. 1 over x squared, 1 over n squared. So 1 over n squared, are we expecting that to converge or diverge? Converge. Yes, converge because it's 1 over n squared. That's the p series. P bigger than 1. So we're expecting this to converge. So your an is n squared plus n minus 1 divided by n to the fourth plus 4n squared minus 3. Bn is what we are interested in as 1 over n squared. And we know that summation of Bn is going to be convergent by P series. So now we do the limit. N goes to infinity. You have an divided by bn. So an is n squared plus n minus 1 divided by n to the fourth plus 4n squared minus 3. everything divided by 1 over n squared. When you deal with a double fraction, you get the limit n to the fourth plus n cubed minus n divided to n to the fourth plus 4n squared minus 3. And now it's calculus 1. You know that you just look at the highest exponents and the limit is 1. So we write the answer, and the answer says, since limit of an over bn is equal to 1, and summation bn converges, the series summation of n squared plus n minus 1 divided by n to the 4 plus 4n squared minus 3 converges by limit comparison test. So I'm going to clear one of my confusions, since you are not having any questions yet. One of my confusions when I was a student was, well, why this method even exists? Because it looks like stacking the deck, right? You want this to converge, and then you make it converge. And you want it to diverge, and you make it diverge. Well, no, it's not like that. Because when you look at the form of the problem, it has a lot of noise. This is all noise over here. It has a lot of noise. But that problem is ultimately 1 over n squared. And we know that 1 over n squared converges by this series. So, no questions there. No questions there. So I'm not stacking the deck, making this converge because I want it to converge. If you try this to make it into divergent, the method would not work. If you go and you say, okay, I want my bn to be 1 over n, and then series of bn diverges, you will not be getting a finite value here. Because when you divide by 1 over n, right, this becomes n to the n cubed over n to the fourth, and that's going to be a 0. But if you take a look at your conditions, it says if it's a 0 and this one convergent, but then we pick 1 over n is divergent. So something has to fail if you are making a wrong choice. Now, obviously, if you are just, guessing, then sure. But if you are honestly doing these problems and you're learning the theorems and you know the chart that I gave you by heart, then you would know that one of the conditions, right, for limit test over here says that if you get a limit of 0 and summation bn is convergent. But now I had it as 1 over n, it was divergent, so it doesn't fit number 2. It doesn't fit number 1 because it's 0. Number 1 is bigger than 0, as you can see. No equal sign there. And number 3 is infinity, but we got 0. So, in case that we make a wrong choice, then that wrong choice would not get you the limit to work out. Let's take a look at another problem that we can solve using limit test. Something 16 is awesome. Summation sine squared n divided by n squared from 1 to infinity. Think about this one for a second. Are you expecting this to converge or diverge? Think about it. Okay, so what are you expecting here to happen? Converge or diverge? Oh, test, it's conversation. Come on, let's go. Give me something so I can... Why? Good. Please converge. You had the 50% chance. Well, that's a good odds. Even though odds say that 70% of the time you'll be wrong. But you got it this time. 30% in your favor. Guys, the most sine and cosine can be is 1. So when you see series with sines and cosines, except in 2 cases, you can ignore them. Just cross them off. Because that sine square on top can at most be 1, and the lowest it can be is 0. So it doesn't really contribute to convergence or divergence at all. So technically what you have there is 1 over n squared. And 1 over n squared converges by p series. When you mush all of this into a limit, it's not going to be good because you will be taking limit of sine squared. But the direct comparison in this case should do the trick. So I'm expecting these to converge because sine n is bounded by 1. That's the statement that technically erases sines and cosines from these problems. So my an is sine squared n over n squared, and my bn is just 1 over n squared. Summation of bn is a convergent by p series. So what do I do? Well, as I said, the limit comparison would not be a good thing because you will be taking, if you try to do limit, n goes to infinity of sine squared n over n squared over 1 over n squared, you're just going to get limit n goes to infinity of sine squared n. And that doesn't work. So we cross that. And we go with the direct comparison instead. So this is one of those rare situations when you must use direct comparison test. As I said, 99% of the time you can use limit, and then some problems just to be annoying, right? You get to use this one. So we need to show remember, an needs to be trapped by bn for convergence, so an less than bn. Now, your an is sine squared n over n squared, and your bn is 1 over n squared. Well, this is already established because this sine can at most be 1, and most of the time is less than 1. So it's already established. It's established here as well. So when I write sine squared n over n squared, is that smaller or equal than 1 over n squared? Multiply both sides by n squared. You get sine squared n less equal than 1. That's true statement all the time. Because your answer for sine has to be number that it's at most 1 or less than 1. And when you square, you even get a smaller number. Let's say, what's the sine of pi over 6? Sine of pi over 6 is 1/2. And when you square that, you get 1/4, right? So all of those values are going to be smaller. So now answer. since an is smaller than bn and summation of bn converges, then the summation of sine squared n over n squared converges by direct comparison test. So that was problem 16. One more and we'll go take a break. When we come back, alternating series. Problem 26, summation 1 over n square root of n plus 2. Try this, talk to your friends. Are you expecting convergence or divergence? Sorry? Convergence. Why? Yes. The overall exponent over here, when you eliminate the noise, which is plus 2, is 3/2. 3/2 exponent is convergent in P series. Very good. All right, try to finish the problem and write the answer at the end. We have to vote on the test tomorrow, so keep thinking because of the quizzes. let's take a look. So as we said, when you eliminate the noise, what you have there is n times n to the 1/2. So 1 plus 1/2 is 3/2. So we will be comparing this to Bn 1 over n to the 3/2. Now summation of Bn would be convergent by P series. So if that's the case, we can work on either direct or limit. Let's do the limit because limit works most of the time. We have our an divided by this one. And then we use algebra to get n, the 3/2 divided by n square root of n plus 2. So now these will cancel. And 1/2 would stay. And what you would get is the limit n goes to infinity of square root of n divided by square root of n plus 2. Now you can use that in a single square root is the n over n plus 2. The property of limit can kick square root outside. That's the last rule you had on the limit rules in Calculus 1. And you get square root of 1, which is 1. So L equals 1. That's the first line on our list of rules. And we have a convergent for Bn. So answer, since limit n goes to infinity of an over bn is equal to 1, and summation bn converges, the series summation 1 over n plus 2 converges by limit comparison test. Again, the sentence in red is not optional. It carries points because that is the answer to the entire question. It shows that conditions are fulfilled and which out of choices, right, out of 3 choices in this case, which choice is the one that is present. There are a whole bunch of different problems that you guys can enjoy here. Some of them will require you to shovel algebra around a little bit. Ooh, problem 19 was on the exam at one point, I remember. It was. I'm not going to solve it, but we can at least talk about it. It was on the exam at one point, I know for sure. Summation 4 to infinity. 1 plus cosine squared n divided by n minus 3. Just by looking at it, converge or diverge? Why? What? We said the cosine doesn't matter. It's the only thing you can actually completely erase and the problem is still the same. Why? Harmonic series 1 over n. Very good. Diverge by comparison 1 over n. Cosine can at most be 1. Therefore, the numerator can at most be 2. So numerator is anywhere between 1 and 2. And we don't really care how much it is. So you're technically having, let's say, at most 2 over n minus 3, and that in comparison to 1 over n, which is harmonic, it diverges, right? The whole problem diverges. So this was one of the exams, and literally should take 2 lines to solve. I mean, you've seen these series. The whole thing is to, unless you have the integral test, right? Then it's years. But you've seen P series. You look at P and you know it's bigger or smaller than 1, right? You look at geometric series. You look at R. Is it smaller or bigger than 1? Right? Divergence test. You take the limit of the sequence AN. If it's not 0, boom, diverges instantly. These tests are jokes. If you know the test, which means you have to memorize the sheet, and you can literally solve exam in 15-20 minutes with writing out integral test. One of the problems must be integral test. The test is doable in 20-25 minutes if you know everything like this. Now, obviously, all of this stuff is foreign because it's discrete mathematics. We don't have continuous and things that you are used to. So it's going to take some time of adjusting and figuring these things out. So let's take a short break. When we come back, it's sweet and to the point section on alternating series.